Started here. I'm Michael Barclay. Welcome to Mapping Uncharted Territory, Predicting Evasive Tradecraft with Cartographer. My professional experience is primarily on the blue team side of things. I've worn a lot of hats on that side of the field, from SOC operations, incident response, threat intel. Currently, I'm the architect for defensive services at Spectre Ops. In terms of academic interests, I'm mostly interested in Windows internals. I'm very Windows heavy in terms of what my interests are, and specifically reverse engineering work. If you ever want to reach out, my Twitter is just my first and last name with an underscore at the end. And before I really jump into the actual talk today, I do want to do a couple shout outs here, specifically to Jared Atkinson and Johnny Johnson, two of my coworkers at Spectre Ops, who are doing a lot of research parallel, if not exactly the same as what I'm going to be talking about today. And we've kind of all been collaboratively working towards the conceptual underpinnings of the project that I'm going to present today. And I also just want to give a quick shout out to Evan McBroom and Lee Christensen as well, who have always been extremely patient in answering very, very specific Windows internals questions that I've come across while putting this whole project together. So first, I'm going to start talking about some conceptual kind of concepts and underpinnings related to detection engineering and evasion and developing more evasive tooling in Tradecraft, and how these are actually kind of predictions about what we think the other side is going to do or already has done. I'm then going to introduce a web application that I've put together to kind of show how you can apply this conceptual model. And I'm going to talk a little bit about the future of that web app and the project as a whole. And then I'm going to do a really quick demo at the end, but the web application is live right now, so I will give you the URL for that as part of this talk. So information security is an inherently adversarial problem set. Attackers develop offensive tradecraft and the tooling to implement that tradecraft, and defenders implement some set of protective controls and detection strategies in response to that. And attackers then pick that up and do the same thing. They modify their tradecraft in response to whatever controls defenders have implemented, or that they at least think defenders have implemented. And this feedback loop continues indefinitely, I guess, until we decide to go back to pen and paper. But there is a kind of cyclical innovation cycle that happens in information security, where we really only progress by way of trying to respond to something we believe is true about what the other side is doing. But these predictions, and we are all in the business of making predictions, whether we're on the red or blue side of things. We're in the business of making predictions about what we think the other side is doing, and these predictions suffer from uncertainty because the problem set is very uncertain. So before we get into some of those sources of uncertainty, we should talk a little bit about what a prediction actually is. And a prediction is some estimation of the likelihood of some future event occurring, right? And I like to think of detection rules, for instance, from the blue team perspective, as a prediction in and of itself. And when we make predictions about anything, let alone just building detection rules, or some other examples we'll get into in a moment, we have to make assumptions about the world around us, because the world is complex. There's always going to be unknowable things that we have to say, we think this is true, and act accordingly, right? And so when we're building a detection rule, for instance, we have to make assumptions about two main categories of things. So first, the nature of contemporary tradecraft. What type of tradecraft is likely to be employed in my environment as a defender if someone were to gain illicit access to it? Not just what techniques, but what specific procedures, what do those procedures actually do? What do the tools that implement those procedures actually do? And I have to kind of hang my hat somewhere and say, this is what I think is relevant to defend against in my environment. And similarly, even if I make a correct assumption about exactly what subset of tradecraft is going to be employed against me, I have to make assumptions about what type of telemetry that tradecraft is likely to generate as well, which is sometimes a more uncertain problem, sometimes a more certain problem, depending on what type of telemetry source you're talking about. Similarly, attackers end up making assumptions about essentially the same sets of information. when they're deciding what type of tradecraft to adopt in the middle of a engagement or operation, or when they're building new tooling. And I look at tooling itself, any given particular offensive tool, as a prediction, just like how I think of detection rules as predictions. And like I said, they make the same kind of sets of, they make assumptions about the same types of problems, but they do so in reverse. So attackers are concerned with selecting tradecraft and tooling that is applicable to a specific environment and which they think will achieve some specific objective that they think is relevant to their operation. And they also seek to select tradecraft and tooling that's less likely to be detected or prevented by security tooling, which requires assumptions about what can and cannot be observed by the security products that are likely to be employed in the environments they're operating in. But assumptions, as necessary as they are to making these types of predictions, they suffer from uncertainty. And if we don't address uncertainty properly, if we don't make at least correct or defensible assumptions when we're making our predictions, the tools and the detection rules that we end up creating are going to be inaccurate. And as I was talking on the last slide, we're dealing with two main types of uncertainty. Uncertainty related to tradecraft, which in and of itself is a Herculean effort to just identify what current tradecraft looks like, let alone in a specific environment at any given time, what type of tradecraft is likely to be employed. Threat reports are fantastic, but they're probably just a small portion of what is currently being employed, let alone what is possible in general. Similarly, telemetry is a huge source of uncertainty for both attackers and defenders. A lot of the telemetry sources that we have in our IT environments are incredibly opaque. They're difficult to understand exactly how and why they log one action and don't log another action. It's difficult to figure out if I were to call a specific API function or interact with a specific securable object, whether that will or will not generate telemetry as an attacker. And if we really want to begin combating these sources of uncertainty, we have to start by documenting currently known tradecraft in a way that is fundamentally comparative, as I like to think about it. If we were to take all the tooling that implements a given technique, we need to have some basis to consistently compare the differences and similarities between all the distinct procedures for that technique to have any chance of predicting what future innovation, let alone coverage for currently known tradecraft, might look like. And to help combat this uncertainty, I've developed a web application that I call Cartographer that helps to predict possible procedures for a given technique to reduce, like I said, both types of uncertainty. This web application is still in very early stages content-wise, but I've worked really, really hard to tighten up the data model that it's built on top of to make sure that I am covering the essentially important and essential pieces of information that you really want to know about a given procedure for a given technique. As we'll see when I demo it, when I give you all access to the currently live version, it's limited in the techniques that it covers. It's really one main example with a bunch of procedures outlined for that particular technique. But the overall goal is to consider what is possible rather than what is just observed when we're building detection rules, when we're selecting already existing offensive tooling to use on a like adversary simulation or red team engagement, or deciding when to develop new tooling entirely. So let's go ahead and jump into the data model that underpins Cartographer. So tactics, techniques, and procedures has essentially become the de facto model for describing tradecraft in the information security industry. But the issue here is not that TTPs are inaccurate or a bad model to use, but that they're fundamentally categorical labels. They are not descriptive of the underlying actions that take place when you carry out a specific procedure. And furthermore, there's no real clear definition of what a procedure actually is. Sometimes it's a tool, sometimes it's a specific command with specific command line arguments. Sometimes it's just kind of a general narrative description of how you might approach a specific technique. And This makes it extremely difficult to compare the distinctions between known procedures for a given technique, let alone to say, I know when I've written a detection rule that covers all the procedures for XYZ technique, or whether they're alternative implementations of a technique that you want to execute while you're on a red team engagement. So in an attempt to provide some kind of widely applicable order to the TTP model, Cartographer defines a procedure as an ordered set of operations that, when combined, achieve some specific outcome. We can kind of see in this diagram here that if we move down from the tactic level to the technique level, we have some number of distinct procedures. This is just a very small subset of the known distinct procedures for the technique shown here, which is LSAS credential dumping. But what I want to bring your attention to is this very bottom row, which is the operations layer. So if we look at, for instance, direct access and read implemented by the Mimikatz module, secure LSA logon passwords, what I like to think of as, the canonical example of LSAS credential dumping. We can see 3 operations here: enumeration of currently running processes, access to lsas.exe itself, and then actually reading from lsas.exe virtual memory. So a definition of procedures that involves the word operations isn't very helpful unless I also define operations for us. And I think of operations as an action that targets some object. And what this ends up amounting to is we have kind of a schematic or shorthand for what an operation is that is a pair of an action targeting some object. And obviously these actions have to be specific and appropriate for the object that they act on. We might be able to write to a registry key value, for instance, and we can transact to a named pipe, but we can't really transact to a registry key value, right? These don't make sense. So there is some kind of implicit order to this model of approaching operations that build up into procedures to techniques to tactics. There's a good amount of more work to be done, in my opinion, as far as the way the data model currently stands, to really kind of establish an exhaustive list of these action and object pairs, and to kind of rule out some weird edge cases that pop up. For the most part, as far as the examples that I've covered so far while building out Cartographer, this objects almost entirely refer to what Microsoft and Windows developers consider a securable object that has stayed true for the most part. But there is kind of this lingering question in general of how deep down should we really go when we say this particular action is representative of an operation. For instance, obviously creating a file is an action object pair that is worthy of taking note of as an operation that a given procedure has to implement. But what about parsing memory bytes that are already placed in a buffer, right? It's not really generating telemetry. It's all happening within the memory of the calling process where our tool is running, and the question still stands. And I think I'll find more examples that push my definition of operations a bit more. But for now, you can think of objects largely as securable objects as defined by Microsoft. And an operation is carried out by invoking some specific function, but there's rarely only one functional path to carry out a given operation. So these are just a couple of very obvious, kind of off the top of the head examples. We can call reg set value A to write a registry key value. We can create a file, create file W. We can open a handle to a process with calls like nt-open process. But what's important here is that everything above the operational layer, like I said, they're fundamentally categorical labels, but they're not descriptive of the underlying actions that attack tooling implements. And functions really are where we define what is and is not possible and offer us a concrete definition of what it means to create a file, for instance. It is where the bulk of the analysis that goes into developing content for Cartographer, and in my opinion, really defining what Tradecraft is, actually occurs at that functional level. And real quickly, just a couple of observations I've made while building out content for Cartographer is that tools that implement the same procedure often call different functions for a given operation, and these choices often have a direct impact on the telemetry that's generated by a given tool or by a given procedure. And this is because a lot of, especially native logging, occurs within the context of a specific function. There are function calls that are needed to, for instance, write to the Windows event log to write data to an ETW provider. These happen in the context of a specific function. The developers at Microsoft who wrote, the read virtual memory function, as it's defined internally within the Windows operating system, had to decide where to generate telemetry. And similarly, as the last talk mentioned, EDR providers, for instance, using function hooking and kernel callbacks, those are also scoped to specific functions as well. And a really big takeaway that I hope y'all remember walking away from this talk is that some operations are fundamentally more important than others. And when I was talking earlier about that cyclical innovation between attackers and defenders, where innovation is almost always a response to some action from the other side, we see this cyclical innovation kind of center around specific operations within a given procedure or within a given technique over time. And when we write detection rules that we often kind of name or describe as targeting a technique, what we're really doing is targeting specific operations within specific procedures for that technique. And I'm going to go through an example here where we can kind of see these observations play out. And there's a lot of other very well-known techniques where we see these observations play out as well. But I chose to talk about LSAS credential dumping today because I think it's generally very, very well understood. There's a lot of tooling that can be deemed as LSAS credential dumping, but I'm going to take two really well-known distinct procedures for this technique and dive into those a little bit to show you kind of how Cartographer actually represents a given procedure for a technique. So the first one is what I like to think of as direct open and read. This is represented by, again, my canonical example of LSAS credential dumping, Mimikatz Secure LSA logon passwords module. Even if this isn't employed a lot in the wild anymore due to modern LSA protections, it's still a good example nonetheless, and I hope I can prove that point to you here. The second procedure I want to talk about is handle duplication. So instead of directly opening a handle to the running lss.exe process, we can attempt to find another process that already has a handle that's open to it and use that instead, duplicate that handle and use that instead. So if we dive into the first procedure here, direct open and read memory, there's really three core operations that have to take place and do take place, and particularly the Mimikatz implementation of this procedure, but also many other tools implementation as well. First is enumerating currently open processes to obtain the process ID for lss.exe. We need that value to call functions like open process, for instance, which is what Mimikatz calls, to open a handle to lss.exe with the necessary access rights. And that necessary access rights is a really, really important part. And we're going to see why here in just a second. But there's some very specific, if you're familiar with how DACLs work or security descriptors in general work for securable objects in Windows, you'll be very aware of kind of this idea that if I want to take some specific action on a securable object on the Windows operating system, I'm going to have to plan ahead and make sure that the handle I have to that object in this case has the necessary access rights. And once I do have that handle with the correct access rights, I go ahead and call my memory read functions, whether that be mini dump, write dump, or read virtual memory, or some alternative. To detail the second distinct procedure, actually duplicating handles instead of directly opening a handle to lss.exe, it gets a bit more complicated, but you'll see it ends up in exactly the same place. So instead of enumerating open processes, we're just going to enumerate currently open handles to identify a handle that, in the case of the tooling that I observed, identify a handle with process VM read access rights assigned to it. This may not be true in all cases. It's more of a down select than a necessary to immediately look for handles that have this process VM read access right assigned to them. It's somewhat rare to have this, so it's just a good down select to build into your tooling. Then we're going to open a handle to the process that has that interesting handle open. Again, we don't know that handle points to LSAS, so we're going to we first have to duplicate that handle while specifying the correct access rights, and then actually make sure that it points to lsas.exe, because the way that we enumerate handles originally doesn't actually tell us where that handle points to until we query that handle directly. I think it's ntquery object is the call that a lot of tooling makes. And then if all is good with that handle that we've now duplicated, we're just going to go ahead and pass it back to those same memory read functions that we called in the Mimikatz implementation of this technique, whether that be mini dump, write dump, or something else. And if we kind of compare and contrast the differences between these procedures, I think this is where this notion of operations becomes really, really helpful, because we can very clearly see that really what's changed here is we're not directly opening a handle to lsas.exe. That's the really, really big one, because that's heavily signatured. There's a ton of open source detection strategies out there for handles that have that access right that point to lsas.exe. But we can also start to think about, from the offensive side of things, exactly what is possible for us. If I'm interested in credential material that's resident in the virtual memory of lsas.exe, by really thinking through operations, I can not only decide what's appropriate to employ on a given assessment, but also to kind of think through what future innovation might look like, whether it's worth the trouble for me to maybe look for additional implementations of this technique as a developer. And this is, in my opinion, an interesting diagram, because if we kind of start at the middle with direct access and read, remember that Mimikatz came out in, I believe, 2010, 2011, something like that. And so we've had over a decade of innovation on LSAS credential dumping procedures. And what we've seen is, both on the offensive and defensive side, a lot of focus on that handle acquisition, actually getting that handle to lsas.exe. On the defensive side of things, that looks like things like LSA protections. You can see on the left-hand side of this, the arrow pointing to run as PPL, where as of Windows 10, Microsoft now gives you the option to have LSAS run as what they call protected process light, which kind of ups the requirements, not to kind of avoid some of the details here, to actually get a handle to lsas.exe, let alone things like credential guard, which make dumping LSAS memory itself kind of not very fruitful. But on the right side of this, we can also see, from the detection strategy side of things, we see a lot of detections focused on, like I said, that the opening of that handle to lsas.exe with specific access rights. And to give a little bit more context here, all the blue circles are either protective controls or detection strategies, and all the red circles represent distinct procedures for LSAS credential dumping. And we can kind of see over time that a lot of tooling spawns out of exactly what defenders are doing at any given time, whether that means protective controls that Microsoft provides for us, or just detections that defenders are employing in their environments in general. And, like I said, more than a decade later, we now have tooling like NanoDump that makes it extremely easy to be very selective about what types of operations we actually use when carrying out a given procedure or technique. You can kind of see here, I've drawn little arrows here to all these Boolean values. These are actually all command line arguments that you can supply to NanoDump that will change how we actually acquire a handle to LSAS. All of these input arguments actually lead to just calling mini dump, write dump, but it's a matter of how we get that handle. And it's really just kind of amazing how this stuff kind of snowballs over time, where it's just kind of piecemeal. Defenders make a change, attackers respond, and vice versa. And then eventually it all comes together into these very easy to use packages like NanoDump. And so I've talked a lot about distinct procedures as a consequence of, some set of operations that a tool might implement, right? And I've talked about kind of variance between procedures in terms of they implement a different ordered set of operations. But I haven't talked too much about for a given operation within a procedure, how they might vary. And we have two main types of resources that represent this intra-operation variation or evasion. First is function maps that show the callable and internal functions that can be used to carry out an operation. So this is really kind of showing what is possible, not necessarily what is observed in currently known toolings at the functional level. Both of these actually involve a lot of manual reverse engineering work to put together. So while you will see an operational breakdown for every procedure covered in Cartographer, not every operation is necessarily going to have a function map and or an abstraction map. And if function maps are kind of designed to show all the possible functional paths, as I like to think of them, that can be used to implement an operation, an abstraction map shows how those decisions impact operating system components, essentially. So this is what a function map looks like. This one in particular is discussing or showing all of the different ways that a developer can write values to write data to a registry key value. And all the circles in red are callable from userland, and all of the circles in black are internal functions or not callable from userland functions. And what's really important to take away here is that even if you start way over on the left in the Win32 API space, you're eventually going to traverse this entire hierarchy down to the syscall level in this particular case. And just a quick note about how functions kind of work in Windows, specifically how Win32 API functions work. But Windows actually provides us a whole hierarchy of functions to abstract away all the messy, ugly bits of how the operating system interacts with kind of kernel objects under the hood. And this kind of diagram here isn't exhaustive of all of the paths that you could take in terms of the different types of functions that are callable or not callable in Windows. But generally, we do see this progression from Win32 API. Some Win32 API functions have IPC mechanisms. So for instance, RPC procedure calls is super duper common. ALPC, just to name a couple. COM probably fits in the definition of an IPC mechanism as well, down to native API calls. So your API functions that start with things like NT or ZW are native APIs, which are often essentially just wrappers around syscalls. And what's really important here is that attackers have to make a decision somewhere in this hierarchy. And that decision may have trade-offs, both in terms of telemetry and in terms of the specific secureable objects that their tools end up interacting with, which I talked a bit about telemetry within the context of a specific function, but there's also telemetry in the context of specific objects as well. And tracing the way that known tooling enters into this hierarchy and what happens after these function calls actually allows us to map out what is possible rather than just what is known. And so to kind of give an example, so this is a very contrived example. I just wanted to use the same function map, even though it's not super applicable in the context of writing to a registry key value. But imagine we have one tool that might enter into this functional hierarchy or start their functional path at the Win32 API, specifically a Win32 API exported from an API set in tool one up there. We might have another tool that calls the native version of this API. Then we might have another tool that skips this operation entirely. It has decided that it can still achieve the same outcome or objective that these other tools do, but doesn't have to call any of these functions. And remember a couple slides ago, I talked about abstraction maps. This is what I meant. So an abstraction map, if function maps are meant to show everything that's possible from a functional evasion level, these are meant to be a bit more about the consequences of making specific function calls. So we can kind of see here on the left side, abstraction map will always have this structure of functions, IPC mechanisms, network layer, and secureable objects. I grabbed this one for service creation because I think it does actually kind of prove the utility of abstraction maps and kind of thinking of things in this term a little bit, but we at the top row we have a list of tools. The developers of these tools have made specific choices about how they want to create a service, right? And if you're wondering, regedit is basically just a stand-in for any tool that decides to jump straight down to the securable object layer and just create that registry key and the relevant values that represent a service on the Windows operating system. But nonetheless, what's interesting here and is not noted is that a lot of the logging, the Windows Event Security logs that people use to actually know when a service created actually happens in this RPC procedure that's here on the inter-process communication layer of this abstraction map. And unless you have, for instance, SACL entries for new key creations on the services key, you're not going to get those events or any events for registry key creation in this services path necessarily, unless you've decided to make sure that you have observability for that particular thing. And you may notice this choke point highlighted on the bottom layer here. And I use this to identify essentially the highest layer of an abstraction map where all known functional paths converge. So no matter how I want to create a service, I'm going to end up creating a registry key. There is, under the hood, there are some trickier ways because services are actually tracked in the memory of the services.exe process, which is the RPC server for that userland processes interact with the service control manager. But the idea here is that if we build our offensive tooling to jump straight to choke points, that represents the most evasive way to interact with this procedure. And similarly on the defensive side of things, if we focus our detection strategies on these choke point layers, we have the best chance of essentially making what I like to call a detection that's resilient to evasion attempts. So I'm going to talk real briefly about the present and future of Cartographer. So the web app is currently up. You can reach it at cartographer.run. I will say it's not very well formatted for mobile. I'm not much of a web developer, and I'm definitely not a mobile web developer. So I would recommend using a desktop. And it's really, all it is a read-only display of all of the data that I've included and dumped into the database and this data model that I've been discussing that powers Cartographer. And really, its current state is a preview. It's meant to just show you kind of how the data model works and what it looks like and how we might want to represent and think about describing offensive tradecraft. There is a lot of future work planned. I do plan to open source, hopefully by the end of the summer, and actually start soliciting contributions from other people in the community. I do have some hurdles to get through before that's really a feasible option, just because of the way that data is input into Cartographer currently and kind of the particularities of the research methodology needed to really build out this content. But I do also want to build a lot more integrations, especially ones that with currently existing projects and repositories of information that cover telemetry relative to specific function calls. I know, like I said earlier, my coworker Johnny Johnson's been working on a lot of this type of stuff, and I want to bring a lot of his work into Cartographer as kind of an automated integration and enrichment whenever I put a new procedure into the database for the app. Also want to build out a lot more docs, blog material, video content, whatever it may be. And like I said, I'm not a great web developer, so I definitely want to make it a little bit more pretty in the future. So there are some challenges to a lot of these roadmap items. It's like I said, it's a very research-intensive content. It involves a lot of tracing a Win32 API function call down to essentially the transition into kernel mode. And this involves dealing with a lot of kind of very low-level Windows internals concepts and services and components. So for instance, a lot of Win32 APIs make RPC calls. There's a bit of a trick to reversing what RPC procedure is actually being called when For instance, there's a Win32 API called NDR client call, which is responsible for actually making RPC procedure calls, and it has a very tricky and weird format of how it takes in input arguments to determine what procedure is actually being called. There's also currently kind of a tricky input format. So the way Cartographer works is that all of the procedures that are defined in the app are built out and input via YAML files, which is a good way to keep content persistent and to make sure that it's kind of human readable, because I am building out all of the data that you'll see here in a second for each of these procedures. But I did structure those YAML files in a very particular way, so I'm going to have to document really, really effectively in order to open source and actually solicit more contributions from the community, which is a goal of mine, like I said, hopefully by end of summer. And I mentioned this a little bit earlier, but there are a lot of very tricky data model edge cases here. A lot of functions implement more than one operation under the hood. So I was showing you the abstraction map for service creation. That's a great example of a procedure that there is essentially one function call, create service W, that implements multiple operations under the hood. It not only creates the registry key that defines a service, but it also loads the record that is responsible for recording that service into the service.exe process. There's also kind of a lot of lingering questions around how granular operations really should be. I also mentioned this a little bit earlier with the example of, obviously, file creation is a distinct operation, but is reading data you've already put into a buffer in memory of the process that your tool is running in an operation? Probably not. Is it significant as a challenge that tool developers have to think about, make choices about, and overcome? Absolutely. But if the goal here is to really describe what is distinct between procedures and offer a way for defenders to think critically about where to build detections and how to build detections, and for attackers to select appropriate tradecraft and determine when to develop new tooling, maybe those things aren't super important. But I'd like to represent them somewhere, but they're probably not operations. So some further reading, we have a lot of blog posts. All of these, except for this last one, are on the SpectreOps blog. But I do really love Adam Chester's blog post about Mimikatz. He talks about SSP injection, which is covering Cartographer. And I recommend this post primarily because I think the thought process that went through it is really, really informative to the type of approach that I'm taking to Tradecraft with Cartographer. And in the future, if you have questions and contributions about Cartographer, again, the repo is not open source right now, but you can always DM me on Twitter. You can email me. And once that GitHub repo is public, you can talk to me there as well and submit issues. But for now, let's hop right into demo. And forgive me if this is messy, just because I know we have, I'm split screen here, so I'm kind of like third person operating this web browser. So this is Cartographer. This is the home page. Really, the main view that you're going to be using is this library view. Very, very simple. You'll be confronted with a drop down that wants you to select the technique. Once you do that, you'll see a number of distinct procedures for this technique populated in this other. So let's go ahead and take a look at, again, the canonical example, direct open and read. Every procedure has a description. You also see all of the other procedures for this technique that Cartographer covers. Again, this is not exhaustive necessarily, but I'm really focused on depth over breadth with this web application currently. And for every procedure, you can use this little drop down to see all of the other procedures, whether for this technique or for another one, that when we talked about those action and object relationships that define an operation, it basically looks for every other operation and any other procedure that has that same object and action operation. So you can get a sense of, what other procedures are opening handles and for what purpose and how. I've also gone, and this is all manual as well, gone out and pulled down a bunch of detection rules, and not only just provided information about them in terms of what telemetry they use or which operation within this procedure they're targeting, but added some comments here and there as well. And just some general detection notes. And these should probably just be called defensive notes in general, because I do also comment on protective controls relative to a given procedure in here. But we can then scroll all the way down to operations, and we can show details. And every operation is going to have a description. Some descriptions are more verbose and detailed than others, with some references related to that operation in particular. And if we do have a function map, we have that here as well. And let's see, maybe I have one. Yes, and here's one with an abstraction map. Again, I included this abstraction map more as an example. You can kind of see here that in the case of kernel 32 read process memory or dbg help mini dump write dump, they basically just make syscalls. So the abstraction map isn't particularly informative here, but like I said, I don't think, and not every operation will have an abstraction map or a function map, but I will try to include them where it seems relevant and useful and informative.